At the end of class last time, I wrote the definition of A cross B, which is magnitude of A times the magnitude of B, two vectors, sine of the angle that is formed between the two vectors. And before we ended, I said, well, by definition, we wanted cross product because we want to find a vector that is orthogonal to both A and B. But if I use that formula, magnitude of A is a constant, magnitude of B is a constant, sine theta is a constant or scalar, the result is a scalar, I'm not getting a vector. So what should it be? Well, the magnitude of the vector that you'd obtain using A cross B. That simply is nothing but the length of the vector that is orthogonal to both A and B. You are simply finding the length. In terms of an application, this is simply equal to the area of the parallelepiped. Do we know what that is? Oh, not that. Volume, parallelogram. Stretch, rectangle, parallelepiped, three dimensions. So you have a rectangle, you stretch it, you get a parallelogram. Of course, the area is still base times height. Regardless of whether you have a rectangle or a parallelogram. So what we are finding here, magnitude of the cross product of A and B, result is a vector. You take its magnitude, you get the length of that vector. Whatever vector that we get from cross product will be orthogonal to both A and B. In a practical sense, that would be the area of the parallelogram. So when you find the magnitude, that must equal to the determinant of some sort. Do you agree? Right? Proportional to the determinant, because you take the rectangle, you multiply by the determinant, you get the area of the parallelogram. It gives you the magnitude, so it is going to depend on the determinant, which means we are going to have a matrix. Good. So your book uses vertical dashes, so I'm going to stick with that. But of course, you can put square bracket or parentheses, entirely up to you. I, J, K are unit vectors, and I am in 3 dimensions. I'm not going to get into higher dimensions. And let's start with the case where I have a vector I plus 2j. (3i minus j). Good. Now the k component is missing. Yes, so I can call it 0. When we write this, we will write it as 1, 2, I component, j component, k component, 0, 3 minus 1, 0. Good. There is a formula for the determinant. Take note. For now, I'll explain this in a second. If you simply consider that part as a 2x2 matrix, what is its determinant? We know the determinant is simply AD minus BC. Agreed. So we will have 1 times -1 minus 3 times 2. 1 minus 6. I will get minus 5, and we're going to multiply by the k vector.
Wouldn't it be -1? Minus 6.
Should go back to algebra or elementary school. Okay. Does that make any sense? Now, I used matrix determinants or computing determinants. I will show you how this is done in a bit. But the idea is you take this element, multiply by the determinant of that part. The determinant is -7, and then I put k vector. Good. When I show you how, hopefully it makes sense. But the reason why I'm bringing this up is that making any sense? Why not, Chris?
I think I'm not understanding why you considered the bottom left section as 1 2x2 matrix.
This one,
Yes.
I want you to just take it for granted for now.
Okay.
I'll explain in a second. But having done all this and having given you a result, I have -7k vector comes from this process. My question to you is, from a very basic perspective, could the cross product of A vector and B vector be that? Why not?
Because you're looking at a space in 2 dimensions only. You can't have it take up space in other dimension.
Right, I'm in 2 dimensions. So I'm multiplying 2 two-dimensional vectors. I'm getting a k component. No, it's not doable. But you could do the same process. We will revisit this once I do the determinant part. We could do the exact same thing. With I vector and j vector. Why not? I'll just go ahead and do this. So that's for the third component. So I guess I'll explain matrix determinants or determinants of matrix right now. So we have plus, minus, plus. Okay. There's a reason as to why. I won't get into details because this is not matrix analysis. So that is the third component. I simply found the determinant of that sub 2 by 2 matrix multiplied by k vector. Got that. Good. Now I'm going to do for I vector and j vector, but before I proceed, you were able to give me the answer the very first day we talked about cross product. I asked you in 2 dimensions, what is the vector that is orthogonal to both A and B? If A is a unit vector in, say, X direction, B is a unit vector in Y direction, what was your answer?
0 0.
It has to be the origin. Agreed? But it's not possible. Well, is that true? So to find the determinant, the first component for I, it would result to I vector, another 2 by 2 matrix, yes? AD minus BC from last time, 2 times 0. minus of minus is plus, 1 times 0. What is the result? 0 I. Switch over to J. We will be adding these. That's how you'd find the determinant for the second column using the 2 by 2 submatrix. Same process, you would treat those two as the columns of the matrix AD minus BC, and then you'd multiply by J vector, but you have to account for the sign. Good? So minus J vector times 1 0 minus, or 1 times 0 minus 3 times 0. You'll have 0 J vector. We will add those two together, and the cross product of those two would simply be 0 I vector plus 0 J vector plus 0 K vector. That's the origin. Does that make sense? So you were right. What is the determinant and why does it matter?
Like you're asking.
No, I'm about to explain. It matters because of the definition of a cross product. Suppose you have two vectors. Vector A that is the same as writing it as A1 I vector plus A2 J vector plus A3 K vector. Yes, okay. Again, we have to be in 3 dimensions or higher. Oops. B1 I vector, B2 J vector, B3 K vector. Yes. Now, our objective here is to come up with a vector that is orthogonal to both of those. Good? That's our goal. I'll call it N. Isn't that what they use in physics? Normal vector.
Yeah.
Orthogonal. That's why I picked N. So orthonormal, orthogonal, they are related in the sense orthonormal simply means an orthogonal unit vector. That's all. So we want to find a vector N so that the vector is orthogonal to both A vector and B vector. That is our objective. Well, how would we go about doing this? We're going to use the dot product. Did we get an idea here? Can I erase this? So you can see as to why we don't use cross products when we talk about 2 dimensions. Doesn't make any sense at all. If we use dot products, if I know 2 vectors are orthogonal, what is the angle between the two?
90 degrees.
90 degrees. If the angle between the 2 vectors is 90 degrees, what would the dot product of the 2 vectors be equal to? 0. So if I'm looking for a vector, I want this. Yes. That is a condition. If n vector satisfies those two, that is, dot product of A with it and the dot product of B with it, both of them are 0, indicating that the angle between them is 90 degrees. That's not great. If I had to write the dot product of A and N, what will it be? You can tell me, based on what I wrote. So dot product here, easy, just multiply components. So we'll have A1 and 1 plus A2 and 2 plus A3 and 3 equals 0. Likewise, the dot product of B vector and N vector is B1 and 1 plus B2 and 2 plus B3 and 3 equals 0. Yes. So I want to come up with an expression for values for N1, N2, and N3, so that those two conditions are satisfied. Okay, so last time when I was talking about matrices, Chris kept bringing it up, linear system of equations. System of linear equations. Well, I've got a system of linear equations. And so a matrix is going to come up somewhere. It is going to happen. But the problem here is you have three unknowns. You have only two equations. In our case, there is one solution that we can't get at. Now, in reality, when we solve a system of linear equations, this isn't something that we would do. Here we can't. What is the process behind solving a system of linear equations? There are two steps. What is the first step? Do we have to play the word game? Go ahead, Andy.
When you isolate one of the components,
Mhm.
well, you would just, it really varies, but usually you bring it over by either adding or subtracting and then by dividing.
Okay. Phil,
You also factor out some.
factor out some. Okay. Guess working. First letters E, last letters N.
Elimination.
Elimination, good job. So we want to eliminate one of the components. I'm going to start with the third component. I can do the first or the second as well. I'm going to start with the third. In order to eliminate, multiply the first equation by B3. Right hand side, nothing is going to happen. Same. You would multiply the second equation by. I want to eliminate N3.
So multiply by A3.
A3. So A3 B1 N1, A3 B2 N2, A3 B3 N3. Those two are one and the same. You know, A times B is the same as B times A. Subtract. That will go away. Agreed. So this is what I will get. B3 A1 N1 minus A3 B1 N1 plus B3 A2 minus A3 B2 plus Oh, my bad, that's it. Times N2. The last one will simply be 0. Agree. Okay. Guess I could have pulled N1 out here. So B3A1 minus A3B1 times N1 plus B3A2 minus A3B2 times N2 equals 0. I want to come up with values for N1 and N2 so that this is satisfied. Good. There is one case that would work.
They could both be 0.
They could both be 0. Well, if N1 is 0, N2 is 0, N3 is going to be 0. So, great job. We got the 0 vector for 3 dimensions. So, I'll call this A times N1, uppercase A. B times N2. Yes. If I choose in such a way that N1 is B and N2 is negative A, that would be 0. Agree? Now that I have A and B, I can find N3. Yes. That you can obtain by plugging it back in one of the 2 equations. If I plug it in the first one, have A1, N1 is simply B, A2, N2 is negative A, yes, plus A3, N3 equals 0. A3, N3 would simply be A1A minus, oops, backwards. A2A minus A1B. Good. I can divide by A3.
Question.
Good. I want you to plug in that in the second equation and tell me what you get. So I'm going to take these 2, which I assumed, that's going to make that 0. That part's clear, correct? If I pick the first component to be B, second as minus A, then that will be satisfied. If I plug in those 2 values in the first equation, I get that expression. The second equation is B vector dot N vector, going to plug in B1 times B plus B2 times negative A plus B3 N3 equals 0. Yes. So B1, B plus B2 minus A, oops, or minus AB2. Would equal 0. Sure, you can rewrite it in another way, like I did with the A's. It's not a big deal. So I end up getting two different solutions. Well, that doesn't make any sense. I solve a linear system of equations, I need to get a unique solution. Why am I getting two different solutions? If you go back to linear system of equations, sorry, system of system of linear equations. Three unknowns, we need three equations, otherwise the system is inconsistent. If you have an inconsistent system, you won't have a unique solution. That is the case that we are at. So how do we rectify this? Well, if I rewrote the first one, can I erase this? N3 times A3 plus A1 multiplied by B. B is that part. B3 A2 minus A3 B2. Yes, plus N2 2. So that's the N2 right in this part. I see what I'm doing. Let me do it this way, my bad. A3 N3 would equal to the right hand side A2 times A, which is B3 A1 minus A3 B1. Yes. Minus A1 times B minus A1 multiplied by B. That is B, correct? So B3 A2 minus A3 B2. Good. One more case. Erase. B3 N3. Move B1 times B to the other side, this to the other side. You can write it as B3A3 equals A times B2 minus B1 times B. So B2 multiplied by A, this is A. Good. And the next part minus B1 times B, which is B3A2 minus A3B2. Good. So all I did is rewrote the components for the third, excuse me, the third component in terms of the other two, I had really assumed that N1 has to be negative of, sorry, N1 has to be B, which is that part. N2 has to be negative A, negative of that part. Good with this side, right? Now, whether I have N1, N2, N3, or call it as N1 I vector, N2 J vector, N3 K vector, they are one and the same. Do we agree? Yes. So suppose I have a matrix of that sort. Yes. I can rewrite this, or not rewrite, get the determinant in this manner. For the first component, C1, I look at the submatrix like that. That's what I started with at the very beginning today. So pick this row, that column, and I look at that. I'll have A2, B3 minus B2, A3. Oops. Yes. Positive sign, negative sign, positive sign. When I get to the second part, minus C2, the determinant of that submatrix. Yes. So A1, B3 minus B1, A3. Yes. And lastly, positive sign plus C3. I'm looking at that submatrix because I'm picking that row and that column. So A1, B2 minus B1, A2. Good. Now, if you compare what we have up there and this, you should see some similarities. Do we see similarities? Yes. When I picked N1, the component N1, N1 ended up being B3A2 minus A3B2. Yes? It's right here. Agree? The second component, N2, is negative A, which is B3A1 minus A3B1. It's right here. Because it is negative A up at negative. Yes, if it had been just, or had it been just A, that would be positive. But since I have a negative A, negative, and A part, naturally, the third component has to be A1, B2 minus B1, A2. You can plug it back in and do algebra. You will see that this is the value that is going to satisfy those two equations. If you're interested, give it a try. I could. So if you take this value, plug it in here, they will be equal. So we got the first component, N1. That is it, N1 or N2? Yeah. N1, N2, N3. Good. Going back to maybe 5 minutes ago, or 8 minutes ago, I asked, well, does it matter whether I write it as just N1 or N1 I vector? He said, no, it doesn't. Agreed. So what I'm going to do, going to replace C1 and C2 and C3 as I vector, J vector, and K vector. You may ask, well, how is that right? Well, going back to this, I vector, J vector, K vector. Yes, those are the basis vectors for the 3D space. If you add and subtract in multiple varieties, you're going to get every single point. And we agreed already that whether I write it as N1 or N1I vector, I'm referring to the same thing. So I, J, K, and the vector A, the vector B. Yes, definition of determinant. So a determinant that's what I wrote over here. Instead of C1, I'm using I vector. Yes. So I vector. In my case, I vector, N1, one and the same. If you don't want to confuse yourself, one and the same. Call it N1, N2, N3, C1, C2, C3, referring to the same thing. So I vector multiplied by that term. Minus J vector multiplied by this term. Plus K vector multiplied by that term will be N vector or C vector. Good. This is what Haley was referring to, the I, J, and K matrices. This is great and all. If we want to represent it as just a simple vector notation without I, J, K, I want to denote, erase this part, yes. I don't want to write IJK. I simply want to use this notation. So what is the first element?
A2B3
A2B3 minus
minus B2.
B2A3. Second element, negative of whatever you see.
Negative.
So you can write it as B1A3 minus B3A1. Last component, A1B2 minus B1A2. Agree? That is the vector which is going to be perpendicular to both A as well as B. Lots of work to get there. Only feasible if you understand the definition of, a matrix determinant. So if you want to find the vector, all you have to do is put IJK in the first row. Put the vector A in the second row, vector B in the third row, find the determinant, that is going to give you the cross product of A and B, yes. And the resulting vector will be the vector that is orthogonal to both A as well as B. And its magnitude is what we had at the very beginning. Magnitude of A times the magnitude of B multiplied by sine theta. Yes? Okay. We'll do a simple problem and then we can extend it. You should know the answer to this already. Any thoughts? So even before you start the problem, you should know the answer. It is simply going to be a vector that is in the direction of the z vector, the vertical axis. Going back to the right-hand rule. When you have two vectors, the thumb is going to point to the direction of the vector that is orthogonal to those two in our regular coordinate space, x, y, up. Yes? So it is going to be a scalar multiple of k vector. If you change this to a unit vector, change that to a unit vector, this is simply I and that's simply j. Do you agree? Those are the unit vectors. So I'm going to get some form of a k vector. Good? We'll see if it happens. Okay. We'll start with the matrix A. See, I'm going back and forth between a line and parentheses. So your book uses vertical lines. I'm used to parentheses or square brackets. Write the first vector 2, 0, 0. The second vector 0, 4, 0. Yes? Plus, minus, plus. I vector. First row, first column would mean we are looking at that submatrix. Determinant of that submatrix, AD minus BC from last time. 0 times 0 minus 4 times 0, 0 minus 0. Yes? If I pick the second column, first row, the submatrix will be 2, 0, 0, 0, same AD minus BC, minus J vector, 2 times 0, 0, minus 0 times 0, 0, yes, plus third column, first row, two times 4, 8, minus 0 times 0, 0. Yes. That's gone, that's gone. All you have is 8k vector, which is nothing but a scalar multiple of the vector, unit vector in the direction of z-axis. Agree? Can't see it. This is simply 8 times 0, 0, 1. 0, 0, 1 is the vector that is perpendicular to both 2, 0, 0 and 0, 4, 0. Are they, can I erase this? So if you set up the matrix like I did, if you find the determinant, we are pretty much finding the cross product. The result is going to be a vector. If you took its magnitude, then you get its length. Yes. What is the length of the resulting vector?
Oh, okay.
A inner magnitude square root of a squared. Besides, it's right here. Yes. So the magnitude of the cross product of A times B is simply A. Good. We want to know the angle between A and B. What do we expect to get?
90 degrees.
Huh?
Isn't the angle 90 degrees? A B of those two.
90 degrees. But is that what we want to test though? If we are finding a resulting vector that is perpendicular to both A and B, what do we need? We need to find the angle between.
That joins the two, that joins the two vectors, like the angle between vector A and B.
So you want to find the angle between A and whatever we found. Let's call this the n vector, right? Orthogonal to both A and B. I want to find the angle between A and N. I want to find the angle between B and N. Both of them have to be
Nice.
90 degrees. Well, what is one way of finding that?
A dot M over absolute value.
So either you show that the dot product is 0, or the angle between them is 90 degrees, right? Well, both of them can be obtained easily using the dot product. Do you agree? Can you get it using the cross product? Absolutely. Too much work. You can either eat a sandwich this way or that way, right? Using a dot product, this pleasurable, not so much. Yes. So we don't want the angle between A and B because we want to verify if the vector we found is in fact at the right angle. Common sense tells us that already. So case 1, we do A vector, no, N vector. Going back to the beginning of class, that was our condition which led to everything. Yes, if that is the case, that condition better be satisfied. Otherwise, my life would be meaningless. Yes, I wasted all this time, and then things didn't work out. Sad. 2, 0, 0. Dot product 8, 0, 0, 1. 0. So A is orthogonal to N, or N is orthogonal to A, one of the same. That was the second condition that led to everything. So let's see if that holds true. 0, 4, 0. 8 times 0, 0, 1. Multiply, you get 0. That works out too. So the vector that we found, N vector, is orthogonal to both A and B. How did we get that N vector? By using the cross product. again, that determinant should give you the area of the parallelogram. Yes, in this case, you have a vector, 2i vector, 4j vector, 2i, 4j, area 8 from last time. Yes, so I picked an easy case. If I pick two arbitrary vectors in 3D space and I asked you, well, find one that is orthogonal to both of them, not so easy, not as easy, unless you use the process, in which case you will find. We will do a problem on that, a case that is not so obvious. Let's pick two vectors, all non-zero components, and find another one and see if it's orthogonal to both A as well as B. Yes, that is cross product of two vectors, and don't forget the magnitude of the cross product is a scalar. That is simply the length of the vector that is orthogonal to both A and B from last time, from today. But we also know that is simply the area of the parallelogram that you have. Later, surface area. Good. Okay.